What if your robot could talk to your phone, send sensor data, and follow commands from across the room? In this module, we'll use ESP32 Wi-Fi to turn local robots into connected IoT devices. You've already built the core robot skills: reading sensors, driving outputs, moving motors, and making simple decisions. Module 1 gave you the electronics foundation. Module 2 turned that foundation into smarter movement and control. Now, Module 3 connects your robots to Wi-Fi, web pages, and dashboards. A robot becomes connected when it can exchange information beyond its own body. An offline robot reads sensors, runs code, and reacts locally. That is useful, but limited. With an ESP32 and Wi-Fi, the robot can join a network, send data such as temperature, distance, battery level, or motion alerts, and receive commands like move forward, turn on a light, or open a gate. Connection makes the robot part of a larger system. IoT is easiest to understand when you picture everyday objects quietly sharing useful information. A thermostat adjusts before you get home. A car uses GPS and sensors to warn about hazards. A weather station uploads live temperature and humidity. A security system notices motion and sends an alert. In each case, devices collect data, communicate it, and help people respond faster from almost anywhere. A connected robot is always cycling through information. Sensors measure what is happening, such as distance, light, temperature, or motion. The ESP32 reads those signals, interprets them, and decides what to send over Wi-Fi. A phone or dashboard can show that status in a human-readable way. The flow can also reverse. When a user taps a control, a command travels back to the robot, and the ESP32 turns it into action, like moving a motor or switching an LED. Before an ESP32 robot can join Wi-Fi, it needs the same basic information your laptop or phone uses. The network name is the SSID, and the password keeps unknown devices out. The router is the hub that lets devices talk to the network, and often to each other. In your ESP32 code, the SSID and password must match exactly, including capitals and spaces. If one character is wrong, the board will not connect. Always use a safe network you are allowed to access. After the ESP32 connects to Wi-Fi, the network gives it an IP address. Think of this as the robot's home address inside the network. If the address is 192.168.1.45, your phone or laptop can use it to find the robot and open its web page. One important detail: this address can change later unless we set it up to stay fixed. Because connected robots can receive commands through Wi-Fi, the network is part of your safety system. Connect only to networks approved by a teacher, parent, or guardian. Keep passwords private and never type them where classmates or cameras can see. Before driving motors, check the area around the robot. If people, pets, or fragile objects are nearby, stop first. For class projects, use simple private networks or basic login names when needed. Safe connections protect your robot, your data, and everyone nearby. Local control means the controller and robot are usually near each other, using the same Wi-Fi router. That makes it a strong beginner choice. Fewer setup steps, less exposure to the outside world, and easier debugging. Internet control works differently. Commands may travel through cloud services, databases, or dashboards before reaching the robot. That allows remote monitoring and alerts from anywhere, but it also adds complexity, delay, and security responsibilities. Start local, then expand online when the project needs it. The ESP32 can act like a tiny web server. It sends a simple control page to any phone or computer browser that opens its IP address. From there, each button press becomes a command sent back to the ESP32. Forward might start the motors, stop might cut power, and light or buzzer buttons can switch outputs on and off. The key idea is that the browser is not just displaying information. It becomes the controller, so students can drive and test a robot without installing a custom app. In browser control, the browser is the client. Its job is to ask. The ESP32 is the server. Its job is to listen, understand the request, and send back a response. For example, tapping a button might send a request like /lead-on, /forward, or /stop. The ESP32 receives that request, runs the matching code, changes the hardware state, and replies. Web control is really a conversation. Browser asks, ESP32 answers, and the robot acts. Communication in an IoT robot goes both ways. A command is the user's instruction: move, stop, open, close, or beep. Sensor data is what the robot measures, such as distance, temperature, light, or motion. Feedback confirms what actually happened, like motor stopped or gate open. This distinction matters because controls alone are not enough. A useful dashboard combines commands with live data and status messages, so the user can make decisions and trust what the robot is doing. Here's a practical example: a smart plant care robot. Sensors check soil moisture, light, and temperature, while the ESP32 shares that data over Wi-Fi. If the soil is dry or the light is low, the system can notify a phone or update a dashboard. It can also respond automatically by turning on a pump, grow light, or buzzer. The key idea is sensing, communicating, and acting as one connected system. A reliable connected robot is designed for failure, not just success. If Wi-Fi drops, it should choose a safe default, like stopping. It should report clear states so users know what is happening. Test range, response time, sensors, and battery early. Keep controls simple at first, then add dashboards or internet features once the basics are stable. You now have the foundation for web-controlled robots. Connected robots can share sensor data, receive commands, and report status through dashboards or web pages. Terms like SSID, password, router, IP address, client, and server explain how the ESP32 gets online. Next, you'll apply these ideas safely and reliably in the ESP32 Wi-Fi robot, then expand into plant care, security, and debugging projects.